In this video, we're going to talk about thermochemistry, which is directly related to thermodynamics, mostly discussing heat, energy, and how that relates to chemical equations, etc. A lot of the things in this intro video are review from Honors Chem. So I'm not going to do a ton of examples. I will go through them. And then if you have questions, you can obviously ask them. But a lot of it you will have seen already. So let's start by talking about the difference between temperature, heat, thermal energy, stuff like that. So if we were to give you these two different blocks and ask you which one is hotter, that is a very easy question to answer. You can see that the one that is 100 degrees is going to be hotter. So the smaller block is the hotter block here. Temperature, degrees, or Kelvin, will measure hotness or coldness. Okay, a lot of times people say that is heat, and it does have to do with heat, but it is not actually the definition of heat. So we'll get into the difference between hotness and heat today. So let's talk about thermal energy. So here you can see these are very close in temperature. The smaller block is hotter, like we just said in the other one. However, the bigger block has more thermal energy. Even though it is slightly cooler, it has more thermal energy. So let's talk about what thermal energy is. The thermal energy is, you can sort of think of it as which one contains more heat. So if you think about this as like in terms of wood, if you have a big pile of wood and then you have just like one log, okay? They can be at the same temperature. They could be in the same room, but the big pile of wood is going to contain more heat because when you burn that, it's going to give off more heat. Okay, so they could be at the same temperature. Let's just say they're in the same room, they're at 25 degrees Celsius. That doesn't mean that they have the same thermal energy. The heat, which we'll talk about later, is the transfer of energy, is there's going to be more in that big pile of wood. Okay, so here's the same idea. These are not the same temperature, 99 degrees and 100 degrees, but they're very, very close. And you can see that the bigger one is twice the size. So the bigger block here is going to have more thermal energy. It contains more heat. Okay, if you were to take both of these blocks of water and drop them into equal amounts of water at both the waters were at the same cold temperature, the larger block would heat up the water a lot more. So this is very conceptual, and we're going to spend this video getting into more of the math behind that and figuring out exactly how much it would heat up the water more. So what we say here is it has a higher heat capacity. So heat capacity is going to be the joules, which we're going to go over exactly what that is in this video, over the degrees Celsius. Okay, so when we say thermal energy or heat capacity, we're saying, okay, we have this energy, that's joules, divided by the degree Celsius. This is not a particularly useful formula, I guess you could say, because it will change based on the mass. So we're going to talk about a more useful formula as we go through this. Heat capacity is shown with a capital C. Okay, so this is a capital C. There's another term we're going to use that's a lowercase c that we'll use a little bit later. So here, which direction would heat flow in order to reach thermal equilibrium? You can see I already drew an arrow here because I'm re-recording this video. It didn't save the first time. So the thermal energy has nothing to do with thermal equilibrium. So that's why this is a little bit of a confusing topic, because all of these terms sound very similar and it takes a little while to kind of wrap your head around it. So don't get bogged down. If I had asked you this question before I started talking in this video, you would have known, oh, it will go from the hotter thing to the colder thing. That is something that you know. So if we had these two blocks, it would go from the hotter one, the 100 degrees, to the 99 degrees. That hasn't changed. Okay, so thermal equilibrium, we're going to talk a lot about what that term means. But all that is it transferring from the hotter one to the colder one. So here we'll go from the small block to the big block. All right, so let's talk about an actual reaction. Okay, so when you burn coal, which is carbon, you produce electricity. We're going to write a balanced equation for the burning of coal. So burning is combustion, or you in the place of O2, and that's going to give us CO2. You probably know that burning coal produces carbon dioxide. That is another topic for another class. Then it says put E on the correct side of the equation to represent the energy involved with this reaction. If we're burning the coal to produce energy, if we produce energy, it's obviously a product, right? So we'll put the energy on this side of the equation. So this is what we would call, as you know, an exothermic reaction because it gives off energy. So I want to go over PE diagrams just a little bit. We've already talked about those. You did them in honor. We've talked about them in this class. So if we have a PE diagram and we're starting our energy of reactants here, and we're using this, the burning of coal. So we have the energy of reactants. You know that the general shape, it's going to go up for the activation energy. And then if it's exothermic, it's going to go down like this. And the reactants will have more energy than the products do. And that's because the reaction releases that energy. So we're going to have the products having a lower potential energy. Okay, so we know that this is an exothermic PE diagram. We've talked about that before. So here, under our different options, consider the amount of energy in the reactants compared to the products. We just said the answer here is going to be that the reactant molecules have more potential energy, and that's because we know this reaction is releasing energy because we're producing it. Okay. Delta H is going to be the amount of energy that is released in an exothermic reaction. So it's the difference between where you start and where you end. This is something called delta H or enthalpy. Okay, we're going to talk about those words as well today. Enthalpy is just the heat of the reaction. So it's literally where you end minus where you started. Okay, it doesn't matter where you went in the highest point. That's activation energy. That's something else. We're talking about delta H. It's this arrow right here. So you can see that it's redrawn here. Delta H is the energy of the products minus the energy of the reactants. Whenever you see delta, it's always final minus initial. Okay, so here is the potential energy. And you can see here that the potential energy is going to be negative. Sorry, not potential energy. The delta H is going to be negative. And that's because if you do energy of products minus energy of reactants, you can see the energy of products is a much smaller number. So whatever that number is, we can put whatever number you want there. Whatever that number is, it's going to be smaller than our energy of reactants. So it's going to be delta H will end up being a negative number. And that's always true for exothermic reactions. And we'll get to that in just a minute. That's in your notes as well. So delta H is negative for exothermic reactions. If we look at the opposite reaction, right here, the opposite of the coal burning reaction, energy is now a reactant because we flipped around the entire equation. That means energy is absorbed during the reaction And the products in this one, the carbon and O2, are going to be higher than the reactants. Okay, so this is an endothermic reaction. And in this case, delta H will be positive because our products are going to be higher than our reactants. So we plug them into that little delta H formula. Products minus reactants is going to give us a positive number for endothermic. And again, that is always true. Okay, so here's a little summary of that. And then there's a little addition. So some of this we've already talked about. Energy is released, we call it exothermic. Delta H is negative. I'll talk about this in a second. When energy is absorbed, it's endothermic and delta H is positive. Okay, you can also see these little reactions to show you that energy in endothermic, we can put it on the reactant side, and in exothermic, it's in the product side. So now let's talk a little bit about the nearby thermometer. The thermometer is going to be measuring the energy of the system. The surroundings. Delta H measures the energy of the system. So the system is the actual chemicals, and we're going to talk a little bit about what's happening there. The system is delta H, it's the actual chemicals. The thermometer is taking the temperature of the surroundings. The reason this is confusing for some people is because the system and the surroundings are in the same beaker a lot of the time. So when the thermometer is taking the temperature, of, like, let's say the water or the solution, that is technically called the surroundings because it's not part of the bonds that are breaking or being formed. Okay, when we say the system, we're just talking about those bonds, those protons, neutrons, electrons, those atoms. So when energy is given off in a reaction, when it's exothermic, that energy has to go somewhere. You can't create or destroy energy, as you know. So what happens is it goes into the surroundings. When energy is absorbed, when it's endothermic, that energy has to come from somewhere. So it comes from the surroundings. And that's why this is a little bit confusing, because people normally think exothermic, giving off energy, the temperature is going to go down because we're losing energy, but not the temperature of the surroundings. Okay, so remember, the thermometer is taking the temperature of the surroundings. So nearby thermometer is surroundings, and that's probably going to be the solution or the water. Nearby thermometer here, again, surroundings. So in an exothermic reaction, the system is giving off energy, it's releasing it, so the surroundings, the temperature goes up. In endothermic, the system is absorbing energy, so the temperature of the surroundings goes down. So if you were to use a heat pack that you can buy at CVS, and you activate it and it gets warmer, that's an exothermic reaction because it's releasing heat into the surroundings, and then you feel it getting hotter. So exothermic reactions get hot. If you get an ice pack and you crack it and you shake it and that gets colder, that's an endothermic reaction because it gets colder. So it's a little bit confusing because the enthalpy, the energy of the system, is different from what a thermometer is going to measure. Because the enthalpy is the actual chemicals, the thermometer is the surroundings. So you just have to keep that stuff straight. So I wanted to go a little bit into this because I know some of you have either taken physics before or are taking it right now. And you've heard a lot about energy and as it relates to work in physics. We don't really talk about work in chemistry. We're going to focus on chemical reactions. So we're really just going to talk about the energy, not what it can be used for. I mean, we will talk about like activation energy and chemical reactions and stuff, but we're not going to talk about what we as humans could do with this energy, what work could actually be done. That's for physics class. So in chemistry, we're going to talk about thermal energy. We already started. Chemical potential energy, we've done that. And electrical potential energy, we will have a unit on that coming up later this year. So we are going to talk about joules. Joules are our energy unit, just like it would have been in physics. Physicists defined joules very differently than chemists do, okay? So we don't care about this KE equation. So in chemistry, it gives you the definition of 1 joule, but quite honestly, we don't really care about that. This is what we care about. You'll see this 4.18 number a lot. 4.18 joules of energy will change 1 gram of water by 1 degree Celsius. That's what we call the specific heat of water, and we're going to get into what that is, and we have a different specific heat for every substance. So for water, 4.18 joules will change 1 gram of water 1 degree Celsius. Okay, so let's get into, like what I alluded to at the beginning of this video, temperature and heat are not the same. Temperature is a measure of kinetic energy, okay? It will measure how hot something is. It's measured in degrees or in Kelvin. Heat is the exchange of thermal energy. So the heat is transferred. The thermal energy is transferred, and that is heat. Okay? Heat can only be measured when it's transferred. So we will use joules. Calories also, calories with a capital C is actually kilocalories. Oops. In terms of science. So when you hear calories, it's calories with a little c is what we talk about as calories. Calories with a big C is what you would hear for food calories. But we're mostly going to use joules. So let's talk about that transfer of heat a little bit and getting us to thermal equilibrium. So if we mix equal quantities of hot and cold water in a perfectly insulated container, which we're going to call a calorimeter, we'll get more into that this unit, the final temperature of the mixture should be. Now the key here is that it's equal quantities and the same substance. If it's equal quantities of the same substance, then your thermal equilibrium will be exactly in the middle. Okay, that's not always true. It's not always in the middle. But if it's equal quantities of the same substance, it will be in the middle. So here we have 75 grams of water at 20 degrees Celsius, 50 grams at 80 degrees Celsius. So we still have the same substance. It's still water, but now we don't have the same amount. So they're not going to have the same thermal energy or capacity. Okay, so when they reach thermal equilibrium, what that really means, what that phrase means, is the same temperature. So just like when we did equilibrium last time, it doesn't mean a certain position, right? It means a certain ratio or a certain formula that you can meet. So here, when we say thermal equilibrium, it can be different temperatures. It doesn't always have to be in the middle, and that will depend on a lot of different factors. So here, if we have more of the cold water than we do of the hot water, we would expect it to be somewhere in the middle, but closer to the cold temperature, because they're going to meet in the middle. They're going to end up at the same temperature, but it's going to be closer to the cold one because we have more of that cold water to start. So let's take a look at this one. So here's an idea, just a little scenario, okay, that is common sense, just because you've experienced this. And this is to the point of what we just said. If you have a freezing cold pool that your friend doesn't want to get into, you can't just run into the house, heat up a teapot of hot water and dump that into the pool and expect it to make a huge difference. It's not going to. And the reason for that is because it will change the temperature a tiny, tiny bit, but honestly, you won't even be able to notice it because the pool water compared to the tea kettle it's so much more water. So you have so much more of that cold water. right? So you know putting just a teapot, even if it's boiling water, a teapot full of water is not going to change the pool temperature because you have so much more of that cold water. And that's something that you would have known before you ever walked into a chemistry classroom. So this is stuff that you know, stuff that you understand. Now we're just putting numbers to it and putting words to it. So let's talk a little bit about this capital C heat capacity. Capital C heat capacity is the quantity of heat required to change a system's temperature by 1 degree Celsius. Q will be heat, which we measure in joules. Delta T is just the change in temperature, so it's final temperature minus initial. Whenever you see delta, it's final minus initial. And we're going to do that in degrees Celsius here. Okay? However, what you see here is the amount of material present, so water, wood, whatever you're talking about. The amount of material present will dramatically affect the heat capacity. And that makes sense. If you have, we talked about this, if you have a giant pile of wood, there's more heat capacity in there. Like it's going to give off more heat than if you have just one log of it. Okay? And that's why this formula, quite honestly, is not super helpful. But there is a variation of this formula that is very helpful, and we'll get to that one as well. So this question brings us to when we have different substances. So you can see here, the amounts are the same. They're both 50 grams. But we have alcohol and hot water. So there is no way at this point for us to know where the thermal equilibrium temperature will be. So we would say not enough information to decide based on these statements. We need more information. So we are going to talk about what that exactly would need to be. So that brings us to lowercase c, which is called specific heat capacity. Specific heat capacity is a more useful value for us than heat capacity because specific heat capacity is going to be a constant for an individual substance. So it will not be dependent on the amount you have, okay? So we can look up these values and plug them into a formula. The problem is that our formula will have amount. So if you look here, our new useful formula that we will use is Q, which is still heat in joules, is amount times little c, specific heat, times delta T. You have probably seen this formula before, and if not, you will see it a bunch. I'll refer to it as the calorimetry formula, the MCAT formula, but it is something that we will use quite a bit. You really won't use the ones above it. You just use the one I highlighted. So you can use this formula for a bunch of different things. So that brings us to a very big assumption that we will use a whole bunch in this unit. We are going to assume that the energy that is released is the same as the energy that is absorbed to reach thermal equilibrium or anything, to reach thermal equilibrium. So the energy lost is always going to be negative Q. The energy gained is going to be Q, and that's just really a convention, but you'll see it a lot. So we just learned that Q can be equal to MC delta T. You'll often see amount. Most cases it's going to be mass, so I just use M. So negative MC delta T will equal positive MC delta T. So the amount of energy that is lost, or heat that is lost, is going to be equal to the amount gained. And then we already talked about what delta T is. So let's take a look at that problem again, now that we have this information. So what you will do here is the water, the hot water, is going to lose energy. So the water will be negative Q. And that's going to be equal to positive Q for the ethanol. We can take a look at that ethanol problem now that we have more information. So what we can do is set the Q of water that's going to be released, because that's the hotter one, to the Q of ethanol that's going to be absorbed. Because water is releasing the energy, we're going to be negative Q. And then that's going to be equal to the Q that ethanol absorbs. So now you can just plug in MC delta T and use the numbers that you know. The mass of water is 50 grams. The specific heat of water is 4.18. Delta T is going to be T final, which is what we're going to look for here. Our equilibrium temperature will be our final temperature, minus initial, which is going to be 80 for water. And then we set that equal to the same thing for ethanol. The mass is still 50 grams. Specific heat we have up here, 2.46. It will be the same final temperature because we're reaching equilibrium, and our initial temperature for the ethanol was 20. I'm not going to go through and solve this. It's just basic algebra, which I know you can all do. So when you do that, you get a final temperature of 57.8 degrees Celsius. I do not know where that one came from. 57.8. So here's a scenario that has to do a little bit, well, it has to do with specific heat. If you wanted to have something to keep you warm and you had two options, either a water jug or a rock, everything is the same. We have equal mass. They're at the same starting temperature. You want to know which one will keep you warmer. It directly has to do with specific heat because specific heat tells you how much heat will be released per gram per degree. Water has a higher specific heat than a rock, so it will release more energy per gram per degree. So if you were in this situation, you would want the water jug. All right, so now let's do some basic calorimetry type. Well, we have a bunch of different problems coming up. This is a basic calorimetry type problem. There will be an opportunity for you to practice these in class as well. So here we're looking for how many kilojoules of energy are required to change the temperature of 36 grams of water from 5 degrees Celsius to 65 degrees Celsius. That is a very basic MC delta T problem. You're looking for energy, so that's Q. All you have to do is plug in your mass, 36 grams, your C, 4.18, and then your delta T, your final temperature is 65, and your starting temperature was 5. You plug that all in, and you get 9,000 joules. Now, joules is your energy unit here because your C is in joules. Okay, so grams will cancel, degrees Celsius will cancel, and you'll just have joules. The problem is asking for kilojoules, so always make sure that you're answering the question. So very easy to convert this. Why do I keep writing random numbers? To kilojoules. So your final answer would be 9.0 kilojoules. So let's take a look at another problem. Determine the starting temperature of hot water when 128 grams of water at 11 degrees Celsius is mixed with 95 grams of hot water and the final temperature is 28 degrees Celsius. So this to me is setting Q equal to Q, right? So we have two waters, one at some temperature we don't know and one at 11. Our equilibrium temperature, so our TF for both of them is going to be 28. So let's start that. The hot water is going to lose Q and the cold water will gain it. So we'll have negative MC delta T for the hot water equals MC delta T for the cold water. The hot water is 95 grams. C, 4.18. And then delta T, the final temperature is 28. And the initial temperature is what we're looking for here. So we can set that equal to the cold water. The cold water is 128 grams. C is 4.18 because they're both water. And then here we would have 28 minus 11. Now here, because they're both water, the C's will cancel, so you can get rid of those if you want. If you don't, and you just solve it that way, that's totally fine too. So when you do this out, you would get negative 95 grams times 28 degrees Celsius minus T initial equals 2176. And when you solve that, you would get T initial is 51 degrees Celsius. So enthalpy, delta H, is the heat of a reaction. Okay, there's a bunch of different ways to talk about enthalpy, and we'll get in more into, we'll do a little bit today and a little bit in the next video as well. So we're going to talk about what is actually happening in a reaction. So we know that endothermic means energy is absorbed, exothermic means it is released. What is happening in the actual reaction is that bonds are being broken and then being formed. So the reactants break their bonds, and the products form new bonds. Okay? When bonds are broken, that requires energy. When bonds are formed, that releases energy. So it all comes down to which one of those energies is higher, the ones that from the bonds breaking or the ones from the bonds forming. That's when you find out if something is endo or exo. So here's a little bit more about it. So this is just explaining endothermic a little bit more. It's the same basic idea. So let's take a look at some reactions. For this reaction, ATP, ADP, which value of delta H of reaction will be recorded in the table below? So where this question mark is right here. All right. So you know that delta H is going to be products minus reactants. So 20 minus 50. So it's pretty easy to see. Negative 30 is going to be the answer here. So this is an exothermic reaction. Delta H is negative, and you can see that the energy of the products is lower. So these are just some kind of complicated charts that really you don't need to think too much about. Okay, it talks a little bit more about why some will be endothermic, some will be exothermic, some, because all bonds breaking are going to be endothermic because they require energy. All bonds forming are going to be exothermic, and it all depends on where those end up in your particular reaction, what the overall delta H is. This, quite frankly, is not that important for you to understand. It's just another visual way for people who need to see a graph or something to understand the endo-exo situation, okay? So you don't need to worry too much about that. So here, delta H for this chemical equation, if we have our energy right here, it is one of the reactants. So we know that delta H is endothermic, right? If it's one of the reactants, the reaction is endothermic and delta H is positive. All right, so now we get into Hess's law, which we have used before, and quite frankly, this one is easier than the Hess's law situation we did before, because before we were talking about equilibrium constants, and you had to remember certain rules. For Hess's law with enthalpy, with delta H, you don't. Whatever you do to the reaction, you also just do to delta H, so it's really straightforward. Okay, so here's a little bit of the rules, but you can see they're pretty much the same. If you multiply one of your smaller reactions by any number, you multiply delta H by that number. So it's not like K where you have to figure out what to do to K, you just do the same thing to H. If you reverse it, you are going to change the sign. If you divide, if you multiply, you're just dividing or multiplying delta H. Okay, so then what we will do, we did this before with Hess's law, if the reaction can be added together, if all the reactions can be added together to your overall reaction, you can also do the same for delta H. Again, with K, we had other rules for that. Delta H, all you have to do is add them. So you just keep track of what you do to each individual reaction, make sure you do that to its delta H, and then at the end, add them all together. Okay. So here, if we want to find our overall reaction, and we go up here, I'm going to do a little, it's kind of confusing, there should be a space in there. So here we have N2O4 and 2NO2 here, okay? In our first reaction, we have 2NO2, but it's on the wrong side, so we should reverse that. So I would write 2NO2, and then delta H for that is going to be the same number with just a different sign, so negative 68. For the second one, N2O4 is already on the correct side and has the correct coefficient, so I'm going to keep it the same. I like to rewrite it again anyway so my arrows line up, but not everyone does. That's totally up to you. And delta H for that one is obviously going to be the same, 10. So if you add these together, these will cancel. You will end up with 2NO2, gives you N2O4, which is what you were looking for right here. And then all you have to do is add the delta H's together. So delta H for your overall reaction is going to be negative 58 kilojoules. Okay, so again, if the chemical reactions are added, delta H is added. It's much easier than some of that equilibrium stuff we were looking at earlier in the year. Okay, so delta H's can have a bunch of different subscripts. You can have delta H of formation, delta H of vaporization, delta H of solution. They're all this basic same idea. So they're all enthalpy of reaction. It's just that they're different types of reactions. So we're going to take a look at delta H of formation first. So this is the kind of thermodynamic table that you can find in your textbook or online. And you can see delta G and delta S we'll get into later in this unit. But delta H has a little degree symbol, and it also has a little F on the bottom. So that just means it's delta H, the F means formation, and the degree means standard conditions. Okay, so whenever you see that little degree symbol on any of these tables, it will be standard conditions. So standard condition means 1 molar or 1 mole in 1 atmosphere. Okay, the F means the substance that's listed. It's a reaction where that is the product, and the reactants are every element in its elemental form. Okay, so I'm going to show you what that means. Elemental form will be an element completely by itself, like carbon would be C, unless it's diatomic. So like oxygen would be O2, hydrogen would be H2. There are some other exceptions, like sulfur is S8, stuff like that. But the ones you really need to know are the diatomics, which you should know from honors chem, and anything else you can pretty much assume it's going to be just by itself. The other thing that's really important about delta HF is that it is for 1 mole of the substance you're forming. So like if we have this stuff up here, okay, this right here is the delta H of formation for 1 mole of this substance right here. So this 1 mole of it is going to be the only product in the reaction we would write here. So let's actually start doing something like that, okay? So if we have butane, we can see that delta H butane is C4H10, it's down here. And so the delta H of formation here is for this reaction. So you take the compound that you're looking up, it's 1 mole of it, and then you break it into its parts. So carbon is by itself, and H, because it's diatomic, would be H2, and then you balance it. Okay? Keeping in mind that you're not allowed to change the subject of this. And then that's your delta H of formation for that reaction. So when you're making these formation reactions, again, you take 1 mole of whatever substance you're looking up, that's your only product, and then you split it up into its elements. So what's nice, we have a lot of these. You can look up these delta H formation tables. There's a whole bunch of them. And you can write the reactions for them. The 1 mole of the substance you're looking up, again, will be the only product. So you see here, for water, this is the delta H of formation. 1 mole is our product. We split that up into H2 and O2. They're both diatomic. And then you balance it, keeping this at 1. So that oxygen ends up being 1/2. Sugar, we have a delta H of formation. Sugar has 3 elements, so we would all be broken up into our individual elements, and then you balance it. So what's nice is that if you use this delta H of formation table, write these formation reactions, you can then use Hess's law to figure out the formation, the delta H of the overall reaction. Okay, so let's take a look at one of these. So here, we have ethane, C2H6. We want to write a reaction for the combustion of ethane. So that's going to be ethane plus O2 gives you CO2 plus H2O. That's just a regular combustion reaction. Okay? And then I'm going to balance it. And if you wanted to do this 1, 7/2, 2, 3, that would be fine. But I'm going to use these numbers for my math. If you were to do it that way, then your final delta H would just be half of the one that I'm going to have because your reaction is half. Okay? So then what we can do is use the delta H values. So I'm going to do this 2 ways. I'm going to do this a long way with Hess's law, and then I'm going to show you the shorter way with just a formula. see that the math is the same. So the shorter way is just doing Hess's law, but in a shortened version of it. So what I'm going to do first is write my formation reactions. Because I have these elements over here. AP will not usually give you that big giant thermo table. They'll give you a small one with just the elements that you need, or the compounds that you need. So for ethane, butane was the last slide. 1 mole is going to be our product. So that's going to be carbon and hydrogen. And then we can balance that with our 1 mole. Okay, oxygen is already in its elemental form. So its delta H of formation is 0 because it doesn't need to be formed. It's in its elemental form. So you can use that if you need to. It would just be 0. But I don't think we're even going to need that here. So then we'll go to CO2. So that's going to be carbon and oxygen for its elements. And that's already balanced. And then for H2O, we have H, and then to balance it, we put a half there. And then our delta H's are right here. So our delta H's for all 3 of these reactions, because they are all formation reactions, are right there. So now we can use our Hess's law. Okay? So for reaction 1, we see we have C2H6 here. And in our overall reaction, we have 2 C2H6 here. So we need to reverse this and multiply it by 2. And then do the same thing for your delta H. So you're going to flip the sign here and multiply this by 2. So we get 170 kilojoules. So now here, our second reaction, we have CO2 right here. It's on the right side, but we need to multiply it by 4. And then we'll do the same thing to delta H. So that comes out to negative 1576 kilojoules. And then for our water one, it's on the right side, but we need to multiply it by 6. And then we'll also multiply delta H by 6. So now we can add the reactions together to make sure that we have the right ones and everything is all set. So the 4 C's will cancel out. The 6 H2s will cancel out. And then we have 2 C2H6. We can add these O2s together. 4CO2 plus 6H2O. And that is what we wanted for our overall reaction. So once we do that, we just add all of these H's together as well. And that is going to be your delta H of your overall reaction here. Now again, if you decided to do this, but with just 1 mole of the ethane, then you would get half of that as your answer because your reaction is halved. So To finish up this video, let's take a look at the formula. So what you can do here, instead of going on doing Hess's law, you can just take the sum of the delta H of formation of the products and subtract the sum of the delta H of formation of the reactants. And you'll notice when I do this, I'm using the same numbers and the same math that we just did. I just don't have to go through the process of switching all the reactions around. So here, let's say, I'll rewrite our equation just to okay. So for delta H of products, we have 4 times CO2. And if you look at, I'm using these numbers up here again. Okay, so that hasn't changed. It's all these numbers. So for CO2, it's negative 394. And then we'll add that to 6 times H2O, which was negative 242. So that comes out to be this. And then we're going to subtract the sum of the reactants. So that's 2 times negative 85 plus 7 times 0, because the delta H of formation of an element in its elemental form is always going to be 0. So that comes out to negative 14. Oh, whoops, that's this. Sorry, that 1452 is the 6 times 242. So that comes out to negative 2858 kilojoules. So same number, easier way, okay? If you're not asked to do Hess's law on the AP test, obviously you should use this. It's much faster, it's much easier, but I did want you to see it, and there are going to be questions that ask you to do Hess's law as well. So I think it's important to know both ways.